Okay. All right, so now then the question is, well, this might actually not be square. Okay, this might not be a square matrix. Okay, in other words, theta dot might be of dimension n, where n is 4 or bigger, whereas omega is 3-dimensional. Same thing here. Right? How do we get the ellipsoid? How do we get the ellipsoid? Okay. All right, so I'm going to show you how to get that ellipsoid. Okay, so let's see. How to get ellipsoid when J is not square. Is not square. Okay, so this is going to require some different tools. Okay, and this is a tool that you're probably maybe seeing for the first time. Okay, I'm not going to give you the whole derivation. Okay, but we're just going to give you the what you need to know. Okay, all right. So what we want to do is we want to find, let's say, let's consider V. Okay. We would like to find the theta dot that maximizes V. Okay, where V equals, say, J of theta dot. Okay, and we also want theta dot to be unit length. Okay. All right, so we would like to find the theta dot, the direction theta dot, which results in maximum V. All right, so if we go back to that ellipsoid picture here, okay, the maximum V occurs, say, in that direction along the major principal axis. Okay, so what's the theta dot that maps to this? Okay, what is it? Okay, so we can pose it as this kind of problem. Okay, so here's the problem: find theta dot. Okay, that maximizes this. Okay, so let's do it this way. So find theta dot. Okay, and remember, theta dot has to be of unit norm. Okay, that maximizes. Okay, so V equals J times theta dot. Right? J of theta dot squared. Okay, so find the theta dot for me of unit length that maximizes this quantity. Okay, so if we can write this out. Theta dot transpose J transpose times J times theta dot. Okay. All right, so let me show you a simple tool for solving this problem. Well, maybe I shouldn't say simple. Let me show you a tool for solving this problem. Okay, so this is something from optimization theory. Okay, it's a very useful idea. All right, so suppose we want to maximize some function f of x. Okay, or x is, say, n-dimensional. Okay, subject to some constraint on x of the form g of x equals 0. Okay, so let's specify f and g a little more carefully. Okay, so f is a mapping from Rn to R. Okay, so this is called the objective function. Objective function. Okay, and G is a mapping from Rn to, say, Rm. Okay, and typically M is smaller than N. Okay, and this is the constraint. Okay. All right, so so let's suppose the solution is given by x star. Okay, suppose x star is a solution. Okay. Then it turns out that x star has to satisfy a certain set of necessary conditions. Okay. X star satisfies following these are called the first order necessary conditions. First order necessary conditions. Okay, and this is a word that's used so often that people just use the abbreviation FONC. Okay, and let me show you what the conditions are. Okay, the first condition is, well, first of all, it has to satisfy the constraint, obviously. So g of x star clearly must equal 0. Okay, otherwise it's not a solution. Okay, and the second constraint is following: df dx x star plus lambda transpose dg dx x star equals 0. Okay. So if there's an x star that's a solution, then x star has to satisfy these two equations. Okay, and you might say, well, what is this lambda? Okay, where did this come from? Okay, so this lambda is something called a Lagrange multiplier. Okay, so what this above is saying is that there exists x star n-dimensional and this lambda m-dimensional, okay, such that these two equations are satisfied. Such that, okay, let's give these equations numbers. Equation 1, equation 2, okay, such that 1 and 2 are satisfied. Okay. Now, if you think about it, these are M equations. Okay. These, and I'm going to show you in a minute what df dx and dg dx are. I'm going to write it all out for you. These constitute a set of n equations. Okay. So total number of equations, m plus n. Total number of unknowns, well, there's x star, n-dimensional. There's lambda, m-dimensional, so n plus m. So number of equations equals the number of unknowns, x star and lambda. Okay. Okay, so let me tell you what these are. Okay. df dx. Okay, so remember f is something that takes an n-dimensional vector and produces a scalar. Okay, so df dx is going to be a row vector, dx1, function of x, df dx2, function of x, dxn. Okay, so it's an n-dimensional row vector. Okay, so it's an n-dimensional row vector. Okay, so that's the definition of df dx. And dg dx, okay, so g is something that takes an n-dimensional vector, produces an m-dimensional vector. Okay, so there's going to be components g1, g2, up to gm. Okay, so dg dx, okay, function of x, is a matrix. Okay, in the top corner we have dg1, dx1. Okay, in the top right corner we have dg1, dxn. Okay, in the bottom left corner we have dgm, dx1. In the bottom right corner we have dgm, dxn. Okay, so we have an m by n matrix. Okay, so this matrix, dg dx, is an m by n matrix. Okay. All right, so I'm basically just giving you this condition without really deriving it. Okay. But the basic idea is that, okay, so when you have, okay, so basic, because if you're like me and you say, well, okay, I'll take your word for it that this is correct, but it would be nice if I had sort of an intuitive, right, explanation why something like this is true. Okay, so in the case of something with no constraints, okay, so if we have, okay, since we're maximizing things, let's do it this way. Okay. Okay, so if you want to maximize this function f of x, okay, where's the solution? Well, this is the solution right here. X star would be here. Okay. So what happens here? Well, the thing to note is that at this maximum, the gradient of f, or the derivative of f, okay, and x star is equal to 0. Okay, so one way to try to find the maximum of this function would be, right, to find the x star that satisfies this. Okay, so this is a case of no constraint. Okay, if we have a constraint, things get a little bit more involved. That's what happens. Okay, so so this is the no constraint case. Okay, now if we have a constraint, we might have some function. Let's look at 2 dimensions, x1, x2. So maybe, okay, it's some, okay, so f of x might be some surface, okay, 2-dimensional surface defined over the x1, x2 plane. Okay, and perhaps we have a constraint, okay, g1 of x1, x2 equals 0. g2 of x1, let's just make it one constraint here. Okay, so g of x1, x2 equals 0. Okay, so let's say g is a scalar. Okay, so g is a mapping from R2 to, say, R. Okay, so what does this define? This defines some curve in x1, x2 space. So it might define some, I don't know, okay, some curve like that. Okay, so this is the equation given by g of x equals 0. Okay, so this implies that we want to find along this curve, okay, the point at which this is maximized. So it might be that. Okay. All right, so at this point, the derivative is not 0. Okay, the derivative is 0 at the peak here. Okay, but at this point, it's saying that this is true. Okay, the derivative plus this lambda times dg dx is equal to 0. Okay, so if I project the derivative here, maybe it points in that direction. Okay, that's the direction in which this is declining at the fastest rate. Or actually, the derivative would be that way. Okay, so that would be the negative derivative. So this would be, so if we project, okay, so this would be minus df dx and x star. Okay, so what this is saying is that, and that's plus df dx, okay, saying that this vector df dx is orthogonal to this vector, which is dg dx and x star. Okay, so these are 90 degrees apart. Okay. All right, so this is not something that you can just think about for 10 seconds and aha, that's obvious. Okay, it requires a little more thought. Okay, but if you want the intuitive picture that goes along with this result, okay, I think this might be helpful for you. All right, so this is what we want here. Okay, let me erase this again. All right, so let's go back to our problem, which was max with respect to theta dot. This, right? Theta dot transpose j times theta dot. Okay, subject to theta dot transpose theta dot equals 1. Okay, that's what we want to solve. All right, so here theta dot is our x. This is our f of x. Okay, so this is our g of x. We have to make sure that, remember, in the original form we have g of x equals 0. Okay, all right, so if we want to map this to our original formulation, x here becomes theta dot. Okay, f of x is this. So, well, let's write it. Okay, it's that. Okay, and g of x is, well, theta dot transpose theta dot minus 1, or the other way, doesn't matter. 1 minus theta dot transpose theta dot. Okay, so this has to equal 0. All right, so we apply the former first order necessary conditions to this problem. Okay, let's see what we get. Okay, so let's write down our first order necessary conditions. Okay, so the first condition is, well, okay, this one we don't even need to bother writing. It's given. Okay, second condition is df dx plus lambda transpose dg dx. Okay, that has to equal 0. So df dx. So take the derivative of this with respect to theta dot. Okay, so you see theta dot once, twice. So it's kind of like theta dot squared. Okay, now, and there's theta dot nowhere else. This is theta. Okay, so don't worry about that. So this is like, think of this as a constant matrix. Theta dot squared. So if we take the derivative with respect to theta dot, what we're going to get is theta dot transpose J transpose J. Okay, plus, okay, lambda transpose. Now I take dg dx. Okay, so take the derivative of this with respect to theta dot. Again, you see this is like a theta dot squared. Right, so there should actually be, I guess, be a 2 down here. Right, because theta dot squared, so, right, squared, 2 comes down. Because there's a 2 here. Plus lambda transpose, now take the derivative of that. This is like a minus 2 theta dot transpose. Okay, this equals 0. Okay, so get rid of the 2's. We get, and let's transpose both sides. We get J transpose J times theta dot is equal to lambda theta dot. Okay, all right, so this is some matrix. Okay, it's n by n. Okay, so this is some n by n matrix. N by n matrix. All right, so if you look at this equation, what does it look like? It looks like AX equals lambda x, which is exactly what the eigenvalue eigenvector equation, right? Aha, so lambda here can be thought of as an eigenvalue of this equation. Okay. All right. So let's call this equation, I don't know, are we at equation 3 maybe? Okay, so if we now pre-multiply three by theta dot transpose, okay, both sides, we get theta dot transpose J transpose J times theta dot is equal to lambda times theta dot transpose theta dot. Okay, all right, so this we agreed has to equal 1. Okay, from the definition of the, it's given, it's a constraint. What's this? This is in fact the objective function. Okay, so in fact, the objective function is the eigenvalue of J transpose J. Okay, all right, so let's put all this together. Okay, what we end up is that, therefore, okay, so let's go back to here. So this is what? This is an eigenvalue. And this is the eigenvector corresponding to the eigenvalue. Okay? All right, so if we want to solve this problem, what we do is find lambda max, okay, which is the largest eigenvalue of J transpose J. Okay, so find that first, and then find the corresponding eigenvector. Okay, corresponding eigenvector. Okay, theta dot max. Okay, and that's your answer. Okay, so if you want to find the ellipsoid in x dot space, this is what you do. It reduces to an eigenvalue eigenvector problem. Okay, and of course this norm should equal 1. Okay, so finding the manipulability ellipsoid, okay, reduces to an eigenvalue eigenvector problem, okay, involving the Jacobian. Okay, so this is how you find the best posture. All right, so if you want a robot to do some operations and you want to find the best posture, where should I put the workpiece so that the robot can do this? If the robot needs to clean a table, do you want the robot to do it this way, or this way, or this way? You want to find this posture? Solve this. Okay? Find the eigenvalues and eigenvectors. So find the theta, okay, such that it results in a spherical ellipsoid, an ellipsoid that's as close to a sphere as being possible.